Video lab for uniform and non-uniform motion by Aubrey Rollins. Uniform motion is defined as the motion of an object when it covers equal distances in equal intervals of time. This, put more concisely, is when an object has a constant velocity. Non-uniform motion is defined as the motion of an object when it covers non-equal distances or travels in different directions in equal intervals of a time span. Velocity has two major components, speed and direction. Speed is the change in position as related to change in time. The velocity of an object will also show the direction of an object in relation to its origin in the time span in question. In other words, how fast something is moving as well as what direction it is moving in. Speed is how fast an object is moving in relation to time. Speed is always positive because it is a measurement of quantity and size. In quantitative terms, speed is the magnitude of velocity. When you graph velocity, the length of distance between time intervals can be measured independently and will have a magnitude. Once magnitude has been determined, the other element of the graph is direction, which can be positive or negative. The direction of the object determines the sign. We see and or experience motion in everyday life, like commuting to school or tossing a ball. To scientifically explore these everyday motions, we need to break those down and assign numbers to create data that we can then graph. This lab explored these types of motion through LoggerPro. LoggerPro is a computer program that can take information from a video, compile that data, and give us graphs to analyze. This is how motion of our everyday life can be studied, explained, and understood in a scientific manner. For the lab, we analyzed two videos. The first was of a toy car moving forward, briefly stopping, and then reversing. The second video was a ball being tossed upwards and falling back down. The videos were each uploaded onto LoggerPro. A Cartesian plane was overlaid of the video. The video was then given scale and then slowed way down so we could accurately punch markers at each time interval. All that data of the position markers in relation to time was able to be compiled into a series of graphs and data tables. From there, we were able to understand things like velocity and speed, position, and time as related to motion of these two objects. For uniform motion, we use the toy car video. Uniform motion is defined by constant velocity. The toy car exhibits uniform motion after it gets up to speed and then maintains for a series of time before it slows to a brief stop. Upon reversing, it reaches the same speed for the same amount of time, creating this uniform motion. The motion diagram here represents the car. Each circle is a position marker. Each arrow is a velocity vector that shows the magnitude or speed of the car as well as the direction. You can see the arrows are each equal in length, going forward for this time span as well as going reverse. This means the toy car exhibited uniform motion. It's the same as if you were to put your car on cruise control if you were driving down the freeway. If you got up to 60 miles an hour, put on cruise control for 20 minutes at 60 miles an hour. For that 20 minutes you were going 60 miles per hour, consistently you would be going in uniform motion. From the graph from Logger Pro, we can see at time 0.2 seconds, the slope was 0.8 meters per second. At 3.5 seconds, the slope was negative 0.8 meters per second. The only difference between these is the positive and negative sign. The positive represents the forward motion of the car, and the negative refers to the reverse motion of the car. The average velocity in forward motion was 0.7 meters per second, shown by this line for the entire forward motion. The slope equaled 0.7 meters per second. The entire reverse motion averaged negative 0.7 meters per second. Average velocity for the forward and reverse motions are the same except for the sign, which shows direction. The slope at the top you can see is 0, and that shows when the car was at a brief rest. Now on to non-uniform motion. The non-uniform motion was explored by the ball toss video. If we remember, non-uniform motion is defined by its changing velocity in a time span, either with speed changes or directional changes. Both. In the video, after the Logger Pro analysis, we were able to see that upon the initial release of the ball going upwards, the velocity vectors shortened as the ball got closer and closer to its max height. There is actually a brief rest before the ball then falls back down. The velocity vectors for the ball when it is falling down get larger and larger as the time goes by before it hits its origin again. This speeding up motion, or also known as free fall. The slowing down motion is shown when the velocity vectors get shorter and shorter. While speeding up, they are larger and larger. On the upwards mark from Logger Pro, we have this data. At 1.8 seconds, the slope of the position time graph was 2 meters per second. Slope, also known as velocity. At 1.9 seconds, the slope decreased, or velocity decreased to 1.3 meters per second. Then at 2 seconds, you can see the slope goes all the way down to 0, which shows the ball is at a brief rest before it goes down from rest into the free fall motion. At 2.1 seconds, the slope or velocity is negative 1.5 meters per second. Remember, the negative sign is showing direction. Second mark, 2.3 seconds. The velocity is now gone to negative 2.6 meters per second. And then at 2.4 seconds, right before it actually hits its origin again, the velocity is all the way up to negative 3.5 meters per second. From this report, we can see there's much to learn from motion. Just from being able to watch and chart a video, we can find things like speed, velocity, and then from there, acceleration and more. From this data, we can start to see patterns and trends. If we are able to predict motion based on this data we gather, it can help us predict motion or hypothesize motion experiments. It's important to understand motion is not one singular thing, and it behaves differently under a very amount of circumstances. But once you have the ability to slow a motion down enough to chart it, you have the ability to really understand what's happening. In our two experiments, we were able to use recorded motion, slow it down, chart and graph, and assign numbers to motion. From those numbers, we were able to have data tables and graph to visually see what those data tables represented and how motion is represented on a graph. This lab was a great introduction into understanding the basic mechanics of uniform and non-uniform motion, as well as becoming familiar with the Logger Pro system.